Good afternoon, everyone. I hope you're having a wonderful day. So I'm going to try for the third time recording this video. Hopefully I can get all the way through it this time. So it says table 11.3 is the energy terms for various types of solutes and solvents. Now we've discussed some in class and some in the last podcast, and we've been talking about polar and nonpolar. So this is a really good summary of that. And we need to remember that the change in enthalpy of step 1 is creating space within the solute, and enthalpy change of step 2 is creating the space in the solvent. And then change in enthalpy for step 3 is the interactions between the solute and the solvent. And then the change in heat, or the change in enthalpy of the solution, is just the sum. A couple points that I want to make is that when we are creating that space in step 1 and step 2, we talked about the energy has to come into the system, so that's an endothermic process. And then the interactions, it depends on what it is. And then you can see the sum of the solutions here. Something that we haven't talked about, we talked about like dissolves like, and so we probably say, well, nonpolar isn't going to dissolve in something that's polar. But we never really talked about that. The change in heat of the solution is going to be large, and it's going to be positive. The heat is going to stay within it because there isn't any dissolving. They're going to maintain their own pieces. And so then no solution is going to form. I hope that you recognize that the polar solvent is still going to be large because of that hydrogen bonding. Now, when we go down here below, we need to, and I keep stressing this, we need to be able to draw pictures of all of this. So factors affecting solubility, I think you can talk about temperature, you could talk about stirring and pulverizing and all those different things. But the one thing I do want you to add, I just forgot here, for these polar and nonpolar solutes, in general, that if I increase the temperature, so I'm hoping that you're thinking of increasing the temperature of water. You're going to create a lot more collisions. You're going to create a lot more space. But by increasing the temperature, this provides the energy needed for dissolving. Okay, so we need some energy there to break bonds and create some space, and temperature often can do that. So what structurally, be able to draw some pictures. So we have nonpolar dissolves nonpolar. One good substance to always think about for nonpolar is methane. And another one that you will see often is carbon tetrachloride, which we've seen in both cases in my examples that I've been doing. I would hope that you would look at both of them and say, yep, these are both nonpolar. So they're going to have an induced dipole moment, meaning that the electrons are going to slide rapidly to one side and move back and quickly. And so this is going to be the LDF. There is some low-level attractions that are there. So remember that these are weak forces. And in this situation, the molecules are just able to slide between the molecules. There's not a lot of space that's created in here because the forces are so weak. So the solute molecules slide between the solvent. And it seems like a really minor point to make, but they like to discuss this in a situation because the forces are so weak, so we don't have as much energy in the system. Now in step B, or letter B here, it says polar dissolves polar. I hope that you're thinking water is polar, and that should be your number one example. Polar dissolves polar, so we could have water as one of our examples. And here is polar water. I can see that it has uneven charges on each side. And then I could take a look at hydrochloric acid. So again, we know that water, this is slightly positive, this is slightly negative, slightly positive. If I look over here, you can either write that this is slightly positive or slightly negative, or you could use your lines of electronegativity. Make sure that you're very clear when you are drawing this with something, the attractions that are there, that it is this positive and negative charges that are attracted. So water will orientate itself in the way that the attractions are going to be held together in positive and negative. So we have forces here. We have hydrogen bonding, which we talked a lot in class today. You just need to be able to draw that and point where that hydrogen bonding is, and these are going to be strong intermolecular forces. And then if we're going to draw something that's polar and nonpolar, again, you can see up above in the chart that a solution isn't going to form. It's not going to be able to dissolve. So I wrote polar first, so I guess I'll just draw my water one more time. And then a nonpolar substance, go ahead and stick with your methane. So if they ask you to draw something like this, you are showing that this substance is polar, and this one is going to be nonpolar, and there's no attractive forces, so there's no dotted line or anything that I can draw because there is not going to be a solution. No attractive forces, no solution forms. And the chart up above verifies that. Okay, pressure. I hope that we know for pressure now that pressure does not affect a solid or a liquid. It's not going to change how solutions forms with a solid or a liquid. So no effects there. If you can't remember that, make sure you jot that down. Now for pressure in terms of gases, it greatly affects it. So for gases in the substances in the gaseous phase, and can it have a solution in the gaseous phase? The answer is yes. The first chart on the first podcast proved that. So if I increase my pressure, increase in pressure increases, well, there's a bell for you guys, increases the amount of gas that can dissolve. Okay, so this includes Henry's law. You guys have all experienced Henry's law when you have opened anything that is carbonated. So whether it's carbonated sparkling water or a beverage like Diet Coke, they have increased the pressure by changing also the temperature. So Henry's law is saying that the pressure is proportional to the concentration. And C for concentration in Henry's law. And so concentration, the reason they use C is because it could be molarity, it could be molality, and there's also another thing called normality that we aren't really studying in here. But it's just saying that the pressure is proportional to the concentration. So if you think about your can of soda, that gas, that carbon dioxide is trying to rush right out the minute you open it up. Because the pressure is greater on the inside, they've raised that pressure so that they can get more gas dissolved into it. And they also do apply with the temperature. So in solids or liquids, so in situation A, we'll put this for solids and liquids. This is going to be the traditional solubility curve that you have seen and actually did in regular chem when you did your lab. So we have our solubility line going like this, and we know that if I change the temperature, increase the temperature, the amount of mass that I can get in there is going to be greater in terms of solubility. Now, if I do it for gases, the opposite is going to happen here. So I'm going to look at my XY graph again, and the amount of grams, this is grams, not gases. So the amount of mass that I can get in there in 100 grams of water usually is going to be in the opposite direction. So for gases, we want to lower the temperature. If we lower the temperature, then I can get more gases in there. So in terms of our soda can, going back to that, they will adjust the pressure and the temperature to get as much carbon dioxide dissolved in there as possible. Okay, that is what I wanted to cover today. I hope that you are having a wonderful day, and I will see you in class soon.